ones that are completely wireless.
Yeah, the AirPods. Apple's AirPods that don't have any cables. Well, forget about the price of them. I mean, they're probably good quality stuff, but they're not attached to each other. So A, how well are they going to stay in your ears? And B, if you might be jogging. I mean, I do that all the time. I jog, and every time I take a step, when I crunch down to the ground, I mean, there's impact. There's fallout, is what I'm saying.
They ignore earthquake warnings in this area.
Right. So, those things might fall out, but you lose one of the things in the grass or something, right? So now you just lost half of your $150 earphones.
I feel like that would be something that everyone is going to, forget in your pocket in the wash.
Yeah. So we'll see. We'll see what happens. It'll be Apple's AirPod replacement program. Subscription. Be great, just great.
They gotta they gotta have an extra speaker on them. They with your phone, you can ping them like you would with your watch.
It screams.
They just scream.
www.apple.com/store/buy.
Insert your credit card.
Clearly speak your credit card number. All right.
Please speak it out loud.
So let's start segueing towards actually telling our computer what to do. And in order to do that, we need to translate our way of thinking of things to the computer's way of thinking of things and why the computer thinks of things the way they think of things. Okay, so let me just flip through these slides real quick because I had pre-made them and we've pretty much talked about these things. So we've kind of talked about that computers aren't all what computers used to be. We've been referencing smartphones and things like that. So a computer is more than just a desktop or something like that. Now, we don't really need to spend any time on this one. Just we all appreciate that computers are more than just a laptop or a desktop. They're all around us. We've talked about the constraints on performance ad nauseum. So, why do we want to understand organization? Well, we've talked about sequential versus parallel. We've talked about some of the different things that go into this stuff and why understanding what's happening under the hood is important for us to, if nothing else, make good decisions as consumers.
I find it ironic because in that previous slide you had warehouse scale computers, and it's when you think back to really early days. You needed a warehouse to store these things.
That's true. I just immediately got depressed that I ran out of Diet Mountain Dew. What happened?
They're saying you use the points.
Yeah, but do they have Diet Mountain Dew in the machines here?
Some of them.
They took it out of the calf.
Really? Just why?
I guess it wasn't selling. I was the only one drinking it.
That wasn't enough?
It was close. I bet you it was close. Man.
He's been cutting back a little bit, guys. We got to get rid of it.
Yeah, that's true. During the school year, when I'm on campus, I probably drink close to a gallon of Diet Mountain Dew a day.
How do you not get the kidney stones?
Because I only have one kidney, and that one's almost gone.
Do you really?
I was born with just one. I didn't find out till I was 25.
That's something that is more interesting that you didn't find out before then.
Yeah, it was a pretty interesting process how I found out, too.
You were trying to donate a kidney. And
No.
Crap!
I went into the doctor with just random, my stomach was hurting really bad. And what ended up being fixed with Gas X and Advil, it was just constipation pains or something.
Right.
Turned into this 2-month, course where we were hunting for. I had to go to all these different hospitals and specialists. They were injecting dyes and stuff into me because none of my tests were coming back right. They thought there was something wrong in my X-rays. I had some sort of.
They couldn't find your kidney.
But they were assuming they couldn't see my kidney because there was something in there, like a tumor or something. Instead of I just don't have a kidney.
How did they figure it out eventually?
Oh, I think they just ruled everything else out.
Oh, okay.
Yeah, so it was plenty of interesting.
Maybe it's just not there.
They didn't think you wanted an MRI.
Well, they did. Well, they sort of did.
There's only so.
Yeah, I did. They did that, but being big, sometimes they don't get as clear of a picture as they want. But I was walking around in the hospital with a one-size-fits-all medium gown. So I had my my group of nurses that would shield me from others as I'm walking down the hall. So now we're right back to the whole. All he's doing is he's wearing a tie and a Speedo, and he's with the.
I can just imagine that at a hospital. All right, let's go forward.
That's true.
It's like an Assassin's Creed, you just blend in.
Seriously. Okay, so why understand organization? It's important, especially from a innovation perspective and wanting to come up with new stuff. And we've even talked about it just today that adding more CPUs doesn't necessarily make it faster. Sometimes we have to change the way we solve problems. All right, so things to kind of consider. All right, so algorithms were kind of we started talking about assembly some last time, right? So the idea here is that we want to start telling our computer what to do at, we're going to say, for lack of a better phrase, at the atomic level, at a low level, talking to the CPU directly, talking to hardware directly, that type of stuff, rather than relying on a high level language for doing the work for us. What's the advantage of that, do you think? What's the advantage of being able to talk directly to the processor as opposed to having to work through a middleman like Java or C# or something like that?
I feel like we had this conversation.
Well, so what's the answer? What's the real advantage of it?
You yourself get to decide exactly what the computer is going to do rather than going through a compiler which may have kind of a subset or an organization in which it goes through
Well, right. So, but that conversation we had was, is what comes out of the compiler going to be equivalent to what we would write? It's not always going to be the same. But why might we want to just talk to a CPU? Forgetting about whether it's going to come out as equivalent assembly code. What's the advantage of talking directly to a CPU? Go ahead.
The assembler, if you want to make the certain part of the assembler code more efficient, or you want to look back and all, just to concentrate on the particular area of
Okay.
assembler.
So there's certainly reasons for us to optimize portions of a high-level program. But what's an argument for operating completely at the low level? Take high-level code out.
I don't know if this goes against what you just said, but instead of where when you're using like a high-level language, a lot of times you're limited on what you can tell it to do. In this instance, you have like we always talk about programming, like you have a toolbox. In this instance, when you're dealing with the CPU directly at this minuscule level, you have all the tools.
What does it take to actually run a program? So we're on a computer and we double click on a program. What does it actually take to run that program? Does the program, we double click on it, does it run right on the CPU? Or are there things that are happening between us clicking on it and it running on the CPU? There's things. Whether you know it or not, we're guessing there's likely things. What do you think those things are? And whose things are those things? Stranger Things. Stranger Things.
Operating system.
Operating system. Pretty important, right? So operating system is doing a lot of stuff for us. And it's taking whatever we just did and it's doing all the necessary work to get it loaded into memory in the right way so it can execute. Now, are all operating systems created equal? I mean, when we think about operating systems, we're typically thinking about throwing out what's an operating system versus what's a kernel. Like for Mac OS, the kernel is actually the Unix kernel and stuff like that. But when we think about operating systems, we're usually thinking about distribution. So we're thinking about, we have the Mac OS, we have Linux, we have Windows, we have Unix. We're done, right? Something like that. Those are our general purpose operating systems. So is that all that exists? Is that the end of the list of what's an operating system? What would you say is the generic definition or a generic definition of an operating system?
Go between humans, software, and hardware.
Okay. Now, what does that hardware look like? For operating systems like Mac OS and Unix and all those things, the hardware looks like a general purpose computer, right? One of our laptops or a big gaming PC or something like that. But do all computers look like that? Or do we have computers that are far more special purpose than that? Lots of, fewer bells and whistles, built for doing something very specific. Programmable microcontrollers, we talked about it first, but programmable microcontrollers are really a mechanism for us to solve a small problem using built-in software without an OS, right? We become the OS ourselves. But we just say, okay, well, built into that microcontroller is the thing that when you put power on it, it runs this program. That's all the OS knows how to do, is run this. Nothing else. So we just take advantage of that and we edit that piece of it. But there are computers all over the place, in our cars, things like that, that solve very specific problems, yet they're still computers, right? What makes a computer a computer? What do you think is what's the requirement for something to be a computer? Is this a computer? Okay, not a computer. I agree. So why isn't that a computer?
It's empty.
Okay, so if it was a full Diet Mountain Dew, it would be a computer. I agree. So, without spending tons of time on this one question, just generally speaking, what do we think makes a computer a computer? What are the requirements for something to be a computer and therefore needing an operating system of some description?
Has some sort of input-output system, is able to store information, is able to...
Okay, well, so let's stop right there. So if we have something that can't store information, it's not a computer? Okay.
I think that was like a 150 question all the time. It's like, is a calculator a computer? Like a cheapo 99-cents calculator. It can't store information.
Okay.
So it's not a computer.
Fair enough.
Any electronic device can able to take the request and give the response.
Okay. All right. So your definition doesn't include storage, right?
Yeah.
So let's go back to this idea, and this is pretty related to what I'm talking about here. So do you believe in that 150 answer that it needs to have storage?
Sure.
Just because you're supposed to say yes? Or do you actually believe it?
I'm being paid to say yes.
Well, I keep referencing operating systems. At some level, you have to be able to store the operating system, right?
Right.
Even if it's a very simplistic operating system that doesn't do much. Kind of our punchline here with this question is that our gut feeling when somebody says, hey, I have a computer I want you to see, that usually, or you want to borrow a computer, we have an immediate picture in our head that looks like a laptop or a desktop computer. That's what a computer is. But as technologists, we know that computers are much more than that. There are things well beyond those general purpose high performance computers that are also still computers. All right, so and a majority of those, in fact, we can, at some level, we can even say all of those are going to have an operating system of some description. It might be an incredibly simplified operating system, that only allows you to do the two things that computer knows how to do. All right, so computers can be very simple. Makes sense? Because sometimes the problems they're solving are domain-specific problems as opposed to something more complex. All right, so there's computers in soda machines, since we're talking about my empty Diet Mountain Dew. And I wouldn't recommend you try this again, but it is an interesting experiment to... so if you ever try this, do it, then go donate the money to a church or something. What is he about to tell us how to steal something? Christian worldview. Check mark. So when you look at a soda machine, is that a computer? A modern soda machine?
Yes.
At least our suspicion is yes. In fact, the interface to that computer is the buttons. So different makes of the soda machines, there's a code you can put in to the buttons. So what you do is you put money into the machine, and that enables the OS. Then you put in the right sequence of codes, and that puts it into like service mode. Okay? From there, you can dispense soda. You can have it give you a can, and then you can have it return your money. So you can use that soda machine as the computer it was meant to be by putting it into service mode using the interface it provided you. It's pretty interesting. You watch a YouTube video on it or something sometime. But the punchline is we look at it as a machine that dispenses sodas. When behind the scenes there's an operating system in that guy. It's a primitive operating system. It doesn't do a whole lot except respond to a couple of, soda button sequences, right? So if you want, thing A to happen, you hit button 1, 2, and 5. If you want something else to happen, you hit a different sequence of buttons, but it's still an operating system.
Put the money in first.
Find a YouTube video at some point if you would like to experiment with this technology. And like I said, then give the money to a church. Just keep in mind that at some point somebody had to pay for that soda. All right. So we're paying attention again? All right. So bookmark that and you can watch it later. But like I said, don't just steal soda. Experiment with it and give the money to somebody. And then don't do it again.
Here's some money, go do what I just did.
Yeah, we don't want to drop to the level of stealing sodas. At that point, you start having trouble of looking at yourself in the mirror.
To a certain
for other
extent,
reasons.
We've had that, torrenting conversation before. And I feel like probably we've done worse.
Yeah, no, I think there's truth to that, but isn't there also, don't some things just feel too petty?
I don't know, it's free caffeine. Like,
like when I
get a Mountain Dew right now, would you?
Like when I was in Israel this summer, there's a lot of places you would go where there was pay toilets, but there wasn't a person there to charge you. You went to the bathroom, you come out, and there's like a thing with like a picture of a nun on it or something like that. It's like maintained by some church, and the bathroom might have been crap, right? It might not have been a very good bathroom, but it was better than going in the woods or something like that.
Do they have woods there?
Well, they have rocks that are on fire, but so yeah. But
Same thing.
the punchline is unless you just didn't have any money on you, wouldn't you kind of feel bad to walk away from like the little money box there that the nuns have put out to help get them cleaning supplies or the bathroom that you just used? You'd kind of feel bad, wouldn't you?
Yeah.
That feels like a petty thing to do.
I don't know. I mean, then there's Europe where they have the pay toilets, and you're either pay when you go in with a turnstile, or cleaning person's in there staring at you.
Oh no, fair. So then you feel obligated too. But in this case, wouldn't you? I mean, if you had the opportunity to not pay, let's say it was equivalent to an American quarter, and all you had was a dime. Put the dime in, and you could at least look at yourself. And it's like, okay, I didn't have the right change, and I wasn't going to put a $20 bill in there. So.
Yeah, I've had that. It's like when we're in Munich or something. You walk out, the guy's like looking at you. It's like, I don't have anything bigger than a €50 bill.
It's like, it's $5 to use this toilet. It's a good thing I have to go because I'm going to get my money's worth.
I can see you would be like, so how wide are the stalls?
tell me about the accommodations. All right, so point here is what does it take a program to run? And we decided the operating system's involved. So somehow when we double click on something or we issue the command line argument, a command line instruction to run a program, the operating system needs to get involved and ultimately get the processor into the position where it can start launching the instruction set, right? So at the end of the day, when all is said and done, we're going to have a list of instructions that we're going to give that computer. The point is we need to get the computer into the position where it starts at the top of the list and then can start sequentially working through the list. So if we just stop and think about that for a second, if I give you a sheet of paper with 100 lines of code on it, okay, 100 sequential lines of code, and we kind of think that there's probably going to be some programming, logic-y type stuff, so we're likely not going to execute every line of the code. There's probably going to be jumping around, things like that, and with conditionals, we can all kind of identify with that a little bit. All right, so there's 100 lines of code, and we're going to start at line 1, kind of similar to all programs begin and end with main, that type of thing. So we start at line 1, and we start executing one line of code at a time. What are the things that we're going to have to keep track of? If we're kind of, if we have a little piece of paper on the side and we don't want to forget which line of code we're on and things like that, what are the things that we're going to have to keep track of in order to accurately execute the next line of code? This is really getting down to the nitty-gritty of what is a computer.
What resources you have available to you?
Okay, so over here on the table we kind of have a pile of resources. So we have a computation core. So that's our CPU with magic tricks. And so CPUs can be our, the powerful Intel Core i7 general purpose processor all the way down to some very domain specific microprocessor that maybe only knows how to do 3 things, right? A very simple processor could do something like that. So that's one of our resources. Another resource you kind of mentioned is there's going to be some level of memory. In an Intel processor, we might have many registers, many little hardware registers, things that allow us to store stuff. But even in a simple computer, we're going to have a couple, right? You're going to have some storage buckets to put stuff, okay? Let's just keep it at that. So we have processing stuff and storage bucket stuff, all right? Now, after we do each command, each instruction, what changes with this computer? Does this computer have a state associated with it?
Yes.
Because it has memory, right? So if we just say we have 2 little memory locations, and we'll just use the Intel version of this, AX and BX. So those are 32-bit registers, 16-bit registers, Intel architecture. So when we first start out, AX and BX will be just zeroed out. Now we might load some value into AX. Now AX has a value. So after that instruction, the value that's in AX has changed. Now before our next instruction, our current computer has a state associated with it, right? The AX has this value in it, BX has this value in it. Now, how do I know which is the next instruction? Remember we talked a minute ago, we had this piece of paper over here? So I have 100 lines of code. Easy to begin with, because we can just say that the first instruction is instruction number 1 or instruction number 0, depending how you want to count. So that's easy. But now, after I execute the very first instruction, how do I know I need to go to the second instruction? Somewhere I'm going to have to keep track of the current instruction, the index of the current instruction, right? I need to know about that. So initially, that index of the current instruction is going to be 0 or 1, depending on how we index it. Then it's going to go to 2, then it's going to go to 3, and then, with conditional stuff, it might jump to 17 for what's the next instruction I feed the CPU, okay? Now, where do I store that? So again, we're back to this word store, storing things, remembering things. I'm going to have to store that information in one of my storage containers that are part of the resources we have laid out here on the computer, on the table from our computer, right? Okay? Now, do we have a maximum number of instructions that go into a computer program? So I've mentioned that this program that we're running right now might have 100 instructions. How many bits does it take to represent the number 100? So 8 bits can represent numbers up to 255. 7 bits can represent numbers up to 128. So 7 bits will probably cut it to get us up to 100. Okay? What if we need more instructions than 100? Need more bits for that counter? So somewhere, on our piece of paper, we're just going to have a little note. Oh, we're on line 1, then we're on line 2, then we're on line 3, now we're on line 17. What's the next line we do? We're going to have to store that somewhere in a computer. Usually it's called the program counter. Okay, and that's going to have to get stored in hardware somewhere, because even though the CPU might know to look at, when the CPU, if we think about the CPU kind of like a dog, and it's getting ready to eat its next snack, first thing it's going to do is just to say, which snack am I supposed to eat? All right, and it has to check that program counter to find out where does it take its next bite from.
I feel like that's
Potentially pun intended. Its next bite from. Get it?
I think it was more applicable to you in person, because you asked these questions.
Well, I mean, like I said, I took a nap this afternoon. I wasn't feeling that well. I am feeling better, by the way, now. So thanks for asking, by the way.
You're welcome.
Not great, but I've improved since I've gotten here. Usually, when I see somebody like you and I look at the intelligence level that I'm dealing with, it usually makes me feel better about myself.
Happy that I could provide that service.
All that's recorded, so now you have your evidence.
I still don't care. I still have the video of the child in a box thing.
Oh
Saved.
man, that was terrible.
That was a good day.
That was that OS? Was that systems programming?
I want to say it was 350. Oh,
It was OS, yeah,
Yeah.
350.
It was OS.
Have you had an operating systems pass before? Are you familiar
2
with
years
the?
ago.
And we're going to talk about it here, but there's a so this preface you when they giggle. Have you heard of the fork system call before? It's related to what we actually talked about today, where you might split and do two things at once. So what you do is you fork a child. You fork a child process, and then when we were reviewing for a test, I had Keynote up, and I actually had fork a child, and it was inside of a box. So he goes fork a child in a box, and things degraded from there.
This is a great video.
Yeah, that's it.
Because then we got the Brazilian guy to break, finally.
That's true. In that class there was a Brazilian student, really bright guy, but very stoic. Like he just lost it. So, see, Alex has never been stoic, right? You don't even know what stoic means, do you?
The Vietnamese, they don't have a word for that.
All right. So, in any case, we're getting back to our dog example. The dog needs to know what snack it's going to eat next, so it has to reference something that's going to tell it where its next bite comes from. Haha, pun intended. Boom. All right. Get it?
You rushed that one this time.
Yeah, I'm trying to get through some of this stuff so we can keep trucking. All right. So with that in mind, that's one other thing. So we're trying to answer this question of what does it take to actually run a program? So we're trying to play the role of the operating system and almost having an appreciation for how simplistic an operating system can be and still be considered an operating system. We kind of think about this from a human being perspective. We had a little piece of paper that we were just keeping notes on. Which instruction comes next? Maybe I have two. I think in our little simple computer here, we were saying we have two little places of memory we can store stuff, general purpose storage. So now we really have three storage locations. We have the program counter, what's the next line number, and then two little general purpose storage places. So at any point in time, we need to be able to remember the state of the computer. Okay? Now, let's think about limitations of this. So I execute the first instruction. First instruction changes the value of AX. Second instruction changes the value of BX. Third instruction modifies AX based on AX and BX, doing some mathy stuff or something like that. All right? So after each instruction, the state of the computer is modified, right? Now, as you're going through logic in a program, is it reasonable that not all logic is related to previous logic, but might be reliant on that previous logic afterwards? What I mean by that is, do you ever do a math problem, do another math problem, and then use the answers to those two math problems together? That's a thing, right? Sometimes you do two separate problems, and then once you have both solutions, you need to work with that, right? Well, let's think about the constraints we have with this little computer. I have two memory locations. Probably going to be convenient enough to do individual math instructions, right? So we can move things into AX and BX, then we can do add, subtract, stuff with those, storing the result back in another one. So at any point in time, we might have both of those memory locations used up with the kind of the running total in one of them. Well, what happens when we go to do problem number 2? Like, okay, we've done our 6 little math steps to get us our answer here. So answer to problem number 1 is done. So now I'm going to do problem number 2. I'm going to need this guy here in a few minutes, but right now I don't need him. So I'm moving over to problem number 2. Wait a minute. I only have 2 memory locations. I'm going to need both of those in order to do my problem number 2, math. But my answer to problem number 1 is in one of those. What do I do with my answer? Potentially problematic. Pun intended. Make sense?
Is there any temporary just to store?
So exactly. So now we're thinking about how we would solve this as human beings. Well, at the very least, we need another little memory location. Okay? We need a place to put that answer temporarily. Now, as we kind of go down that path, do we recognize that this is going to be a recurring issue? Like, well, I need one more memory location. Now I need another one more memory location over and over and over again. All of a sudden, things don't fit in such a small little space anymore, right? So we have a data structure called the stack. And as long as we can give enough memory to it, so we have to say, okay, well, here's some memory, but we're effectively giving ourselves a dynamic storage location where we can push values onto the top of a stack. So maybe I take out of AX, which was our last answer, I push it onto the stack. So now I know that my current answer is preserved on the top of our stack. Okay? Now the stack might have many things in it, but I know at the very, very top of the stack, and the many things is going to be limited by the total amount of memory they've associated with our stack. But I know the thing at the very top of the stack is going to be my value solution to problem number 1 that was stored inside of AX. So now because I've preserved that, now I can go and I can zero these out and start from scratch, right? I can do my second problem. So now I have my second problem. Let's say the answer is in AX. And now let's say I want to add the 2 answers together. So I would pop off of the stack into BX, let's say. So now I have my second problem answer in AX, my first problem answer in BX that I restored from the stack, and now I can do math with that. Kind of make sense? So we're starting to see this cadence, and as we try to solve more general purpose problems, we have to give ourselves more general purpose registers, more tools that allow us to almost like juggle more things at once. But at some point, we need to have enough flexibility that we don't run into this problem of, oh, I need another hardware register, I need another hardware register, I need another hardware register. That type of thing. Make sense? All right, so when we think about what it takes to run a computer, we're really talking about manipulating memory and executing instructions and making sure that we don't lose data that we had. And we want to do all of that in the minimalistic footprint necessary for the type of problem that computer was built to solve. If it's a general purpose computer, well, we need to give it lots of options, lots of flexibility. If it's a domain specific computer in a soda machine, probably don't need to remember a whole lot of things, but we still need to be able to do it accurately. That makes sense? Okay, so there's some things we need to keep track of, and the operating system is doing that stuff for us. But wouldn't you assume that soda machine doesn't have Windows 10 running on it? At least I hope not. I guess some of those things probably maybe do. But in general, a domain-specific computer like that is likely going to have a very domain-specific operating system running on it. So, having said that, as we talk about kind of how computing actually works today, I guess in general, could we create a very domain-specific operating system for something like that? Could we write a custom operating system built specifically for that soda machine, and it only works with that soda machine for doing the small little tiny problems that the soda machine has to deal with. Is that a reasonable thing to do?
Sure.
Yeah, we can make specialized, think about like clothing, like custom fit clothing, right? So we can make specialized custom fit socks or custom fit shirts for this. This got me off on a segue because, well, it's from an app I just saw the other day. I'm trying to think of the name of the app, but this app claims that they can make clothing for you better than a tailor would make, based on you taking a video of yourself, and you order it, and it's like 100% guaranteed. So I'm testing it. Yeah. So imagine that was an entertaining video. So they have you doing all these, you're standing like this, and you're rotating around, and you're not wearing that much. But yeah, so it'll be interesting. But the point is,
eventually they're gonna sue you for the medical charges of the blind.
Well, what I'm expecting is I'm going to get the shirt that I ordered, and it's not going to come anywhere close to fitting.
They're gonna think, oh, that was just a funky, camera lens. Make them look
Yeah.
bigger.
Yeah. Well, I mean, I just don't know how it's gonna work.
Wear it to class.
Well, because people are, we're very different. People are very different, and not all big people are like big in the same way. Like my legs and stuff and arms aren't fat people legs and arms. My gut is, and then some. So, it's a Max Min type problem. All right, but in any case, so when we talk about these soda machines or something like that, we can create a very specialized, simplistic operating system for that. But how many different, you've heard this phrase called Internet of Things, right? You heard that phrase before? What does that mean when I say Internet of Things?
The internet?
Like self-driving cars sensing the information and sending it to the server to take an action to perform.
Okay. Well, I mean, I think we could potentially throw self-driving cars in there, but when we really say Internet of Things, what we're kind of referring to is, our toasters talking to our refrigerators, talking to our coffee makers, all the things that we've surrounded ourselves with in our lives, all communicating with each other in some way, right?
Making all the digital equipment connected to internet and available to be a single place.
And then related to kind of what we're talking about here is everything is a thing, right? Everything's a thing. So on the internet. So our toaster, who needs your toaster to be connected to the internet? Well, maybe you get a text message when your toast is done. Something like that, so you don't forget the toast. Who knows? I mean, that's
I did see a toaster that prints Star Wars on your toast.
Yeah, I've seen that too. Yeah.
I was really tempted. I have a toaster.
I don't remember where I saw that, but I saw it in one of was it Reddit or something like that?
No, I saw it in the mall, like physically.
Oh, you physically, okay. But, in any case, punchline for us is everything today, or many, many things today, are potential computers that potentially have operating systems that run on them. So the question is, from a practicality perspective, would we write a specialized operating system for every one of those?
Maybe.
Specialized.
Not for maybe every single one. There are probably some that are like close enough to each other that you could tweak certain things in the same operating system that you could just put, make two. They're still different, but you just
perfect. I mean, you're going in the exact direction I'm looking for here. So, this comes back to what's an operating system. So if we think about the Linux kernel, let's say, since that's what we're going to be working in here, if we think about the Linux kernel being the core operating system of Linux, kind of like what runs on a Mac, let's say, that operating system is a kind of a beefy operating system specifically geared for working with, if you're dealing with a modern Linux architecture, dealing with a 64-bit processor. All right, so very general purpose. All right, so that's a heavy operating system. If we think of the Linux operating system as being kind of like a bowling ball. Okay, so it's a bowling ball. That's kind of heavy, right? So we wouldn't want to put that bowling ball inside of our soda machine when all it needs to do is solve the little problem of which button goes to which soda, and making sure you put in the right money, right? It's overkill for that, right?
The bowling ball in the soda machine?
Yeah.
I mean, it would probably get you more sodas if you used it right.
Probably true.
Just watch out for the sharded glass. That's all.
It's true. By the way, I am giving away a free vintage Pepsi machine if anybody wants one.
All you have to do is get it out of your basement. Thing weighs more than he does.
Oh, by a lot.
Yeah.
Yeah. So if you can get it out of my basement, it's yours for free, and it works.
Why are you getting rid of it?
Because it's gonna have to get rid. I mean, it's gonna have to be gone at some point, otherwise it's going with someone with the house.
I mean, you can always just wait until like that one time when the tornado comes. On the top of
And
the
have
house,
them
you're like,
airlifted out.
Yeah.
That's the same day I also install a hot tub in the basement.
You have a hot tub.
In my garage. Because it wouldn't fit in the basement.
Yeah. So you replace the vending machine with the hot tub. Is what you're saying.
Well, I have plenty of space down there. My basement's like 1,100 square feet.
Yeah. But,
Yeah.
like, you just do it in the same like helicopter rental.
That makes sense.
Save money that way.
So we're talking about general purpose operating systems. So certainly we wouldn't need the bowling ball inside of the soda machine. We maybe need something more like a golf ball. For, if we're talking about, the size of an operating system, right? So Windows or Linux is a bowling ball. The thing that goes inside of your toaster is like a marble. Okay, something really tiny. Now,
Less than that.
well, whatever. I mean, we're just talking. We don't also have bowling balls inside of our laptops. Okay, we're just using relative examples here. All right. Now, having said that, would you say that a lot of our home appliances are similar in size?
No.
Toasters, blenders, they're similar size-y type things, right? Okay. Maybe refrigerators become a little bit, they're a class up. They don't need to be all that smart. They don't have to have tons of brains in them. But from a physical component size, a fridge can hold something a little bit larger than a toaster could. But not substantially larger, because you got to consider most of the space in your fridge is taken up by your food. You don't want to give away, tons of real estate inside of your fridge for some, supercomputer to be in there. So realistically speaking, your fridge isn't making that many decisions for you, right? But
my fridge only holds one meal.
but
But it can do my taxes.
it can do my taxes, exactly. All right, so if we took that golf ball size computer or a marble size computer, do we suspect, based on what we know about kind of the power of computing, that clearly a refrigerator or a toaster is going to have to solve far simpler problems than our laptop, right? So we're not putting a Core i7 in our toaster. So instead, we're going to have a very low-powered, not taking a lot of electricity, microcontroller, some sort of processor of some type. But could we marry that? Would you say that if we had 10 different small kitchen appliances, that they potentially could all use the same relatively small microprocessor? Even if it's overkill for it. Even if the microprocessor has 3 hardware registers and the stack has plenty of memory on it and it's more than the toaster will ever need.
I better be getting some really detailed.
But the point is, in terms of its capabilities relative to its physical size, whether, if you put a processor that is plenty small but it's overkill for the toaster, it's not hurting anybody. And then you put that same thing into the refrigerator and... Oh, he was doing it. I recognize that. You're supposed to lean it up against the wall to get the level. All right, we'll wait. We'll watch. He was doing the clothing thing.
Do they have it in Vietnamese?
That would have been really hilarious. Okay, so in any case, we could take that general purpose small microprocessor and put it into a whole bunch of different appliances. Some of which is going to be more appropriate in terms of the the necessary power. Some of them it'll be significant overkill. But I mean, should we create a custom processor for every appliance when we already have a general purpose low powered processor? We'll call it relatively general purpose, that we can put in all sorts of different appliances just because of their physical size. Yeah.
Maybe for the different devices, they put the fixed amount of instructions and particular instructions to follow with respect to the user action. It's not about the different processors to the different devices.
So you're saying modify, so even though it's the same microprocessor, the toaster has an instruction set that's smaller than the refrigerator's instruction set?
Yeah, different instruction sets.
Who dictates the instruction set?
User actions.
So when I say instruction set, what am I talking about?
Like pressing the number 1 button should give something from the one slot from the vending machine.
Okay, so I think what there's two sides of this type of thing. We have on one hand the API provided by the operating system. Okay, that's kind of what.
For the operating system also.
Well, the operating system we can manipulate that some, but the CPU itself, an actual physical processor, has an instruction set with it.
Yeah.
So that instruction set is married to the processor. So if we want to provide a reduced instruction set for a toaster versus a blender, we're going to have to put a different processor in there. So what I'm kind of arguing is that if we already have a tiny processor that's capable of stuff and it's low cost and things like that, why should we have 400 different low-powered processors when we really only need like 5 for different size, classifications, power of devices, right? All right. So effectively, if we just say small appliances, all use the same little microchip, all right, microprocessor. And those same appliances also use it would make sense that rather than write a different operating system for each one, if we already have an operating system that is married to that microprocessor, so like Linux is compatible with the Intel architecture for your Core i7, if we have a mini operating system that's already been written that knows how to work with this microprocessor, can't we just put that operating system in all those machines as well? I mean, the idea is that they're both going to be really, really tiny. I mean, they're for low-powered things, not solving general-purpose problems or solving very domain-specific problems. And kind of related to what you said, Tim, is that many of those things, at least for the types of problems they solve, when we think about them in terms of moving memory from point A to point B and adding and subtracting and stuff like that, they're solving similar enough problems that we can probably pull it off, right, with the right code. So this CPU that has an instruction set with 30 magic tricks in it, on your toaster, maybe you only ever use 3 of them. On your refrigerator, maybe you use 6 of them. So you're not taking full advantage of the processor, but it physically fit. You didn't have to have, and the price was down because they're able to mass produce them and all that stuff. Why create custom processors for each one? Is kind of the punchline.
I want the Mona Lisa on my toast.
Okay.
Don't ask why.
And you could pull that off with the low-powered processor. Trust me, we can do a whole bitmap with that guy. It'll work great. All right, so then we get back to the operating system side of it. So rather than writing a custom operating system, if we already have a small footprint operating system, not a 1.7 gigabyte install of Windows, but a 8 kilobyte install of some small domain-specific operating system that knows how to work with that microprocessor, we could just use that same operating system for all those appliances, right? Okay, so that way we have some sort of standard. So what do you suspect in today's world that operating system likely is, based on the trends we see in computing? I think it's I'll just leave it open-ended for right now, then I'll give you a hint. So when we look inside that soda machine, or we look inside the smart fridge, if we were to be able to get access to the operating system, what do you think it would look like?
Pretty small compared to.
Specifically, you're right. It would definitely be small, but if you had to compare it to another operating system, what do you think it would most resemble?
Linux.
Yeah, it's very, very, very likely it would be a Linux microkernel. Linux has been adapted to have microkernel versions of Linux that run in very small footprints. Because it's been written to run, because Linux source code is available, what you can do is you can say, here's the subset of the Linux operating system that is really required for low power devices. So it doesn't have all the extra fluff for like working with hard drive drivers and things like that. So it's a very minimalistic version of Linux. And so it'll fit in a small footprint. And then you can compile it for that architecture. In this case, the small microprocessor that we're working with for our toaster or for our computer or something, or our refrigerator. So now you have a Linux operating system, which is a familiar operating system. Going to have a familiar command line, so somebody could plug in a USB port to the soda machine or to the toaster or something like that and access the terminal. Be looking at something like this on the soda machine or on the toaster. And they can issue commands to it. They can, look at the log file to see what happened when your Mona Lisa had its face upside down and people were starting to call in an exorcist and a priest and, whoever else. I mean, some people get freaked out by that kind of stuff.
Oh, Christ compels me. I just want eggs.
I just want eggs. All right. So we're going to take a general purpose operating system, look at a small version of it, and then apply that to lots and lots of different problems. Okay. And we've seen it. We saw, Android is based on the Linux operating system. So we saw that 10 years ago, let's say, drop down to the cell phone level. So we took Linux that used to run on computers, and now it's running on cell phones. So then we say, now we have Linux, and it's going to run on a toaster. And then we're going to have Linux, and it's going to run on an Atom. There's a kind of a cool book I think it's called The Invisible Computer. I think that's the name of it.
That defeats the purpose of the computer.
It's a quite fascinating book. I don't want to spend too much time talking about it here, but the premise of the book, I think it's Al Kurzweil, I think, is the author. But it's like The Invisible Machine or The Invisible Computer or something like that. And he kind of talks about the evolution of computers from the beginning through today, and then prediction into the future for how they will keep getting faster and faster and faster.
Is it the idea of like how, to the I don't want to say uneducated person, but to like a person who hasn't studied computers, in many cases they probably wouldn't know that how many computers are in various different things. You see something do something, like you wouldn't automatically think driving a car, oh, this has a bajillion computers in it. Is that kind of where it goes?
Well, yes, but I think it's not just non-technology people. I think it applies to all of us. I mean, things are sci-fi until they're not.
Right.
How many things from Star Trek are common things today? Right? That's like, well, this isn't magic. Even just during any of our lifetimes. The fact that, I can make a phone call on something that's not tethered to the wall. I think that wireless phones have been around for most of your lives, right? Mm-hmm. They haven't for my life. I remember where you had to build up the callus on the side of your finger. You hit the rotary dial, and it hits the thing, and you got to go back, and you hit the thing again. You hear the little numbers. That's how they connected in through analog. I was a little bit ahead of the talking to the operator and call Bill. I didn't have to do that, but
Smoke signals.
Well, yeah, smoke signals, right? So the punchline is that things that used to seem like magic are commonplace today. So what to us today will be commonplace? What's magical to us today that will be commonplace in 20 years? Kind of the purpose of the book, and he gets down to the idea that a computer would be basically ubiquitous with the environment. Basically, it live at the atomic level where you wouldn't even see it, but it would communicate with you through the Bluetooth or whatever, some sort of means of communication with us through wearables or something like that, where we were able to tap into vast amount of computing power all the time. because our computers keep getting smaller and smaller and smaller, yet more powerful, right? So do you just, this is the 6S Plus. So this is last year's awesome.
Garbage phone
Yeah,
now.
yeah. This is my new. On Friday, this will be my new soap dish. Yeah, I'll use your little thing you gave me here. That will help the suds flow off.
You don't want to move that?
Move what?
The thing.
You gave me 2 of them.
Did I?
Yeah, I got a black one too. Because I can't imagine that sticker would work great if you pull it off.
It actually does.
Huh.
It's not bad.
Well, I'll probably use the new one.
Apparently we've messed with interns and say that's how you pick up women. It's like you play with it and they ask what it is and you just, here you go. Like, smooth.
I got you.
And it doesn't work.
Yeah.
Have you tried it?
No, but our last intern did. He came back like, I don't know, he was kind of disappointed.
Well, that's because he's a geek intern,
Yeah,
not a professional beach volleyball player.
exactly.
I'm a geek intern.
But you can also say you're a professional beach volleyball player,
Sure.
right?
You got paid to play beach volleyball?
I have been paid, yeah.
Just told you.
I mean, there's a lot of tournaments out there that you can win money at too.
Would you believe that I've been paid to play beach volleyball?
Absolutely not.
Tennis, maybe.
So
Almost
you're
tennis.
saying you wouldn't believe it?
I could
Oh,
play
well, you'd be
beach
right.
tennis, but you didn't actually make professional. Like,
I played. I was what's called Futures Tour. Yeah, so I played pro tournaments. Futures Tour is what the kind of the top college athletes play in. So think of it like minor league baseball.
okay.
But sometimes minor league, it's probably a little different than minor league baseball, but minor league players get called up to the majors for a game or two or something like that for a series. Maybe they need a fill in, but they're not really fully being called up. They're just kind of being used for a little bit. So I would play like Monday qualifiers to get into the main draw or something like that in big tournaments big tournaments like big small tournaments. Indianapolis Hardcourt Championship. So a tournament like Pete Sampras would play in, but it was really part of his hardcourt season in preparation for the U.S. Open. Where that was like, I was hoping to get into the draw type thing. So I would get up against one of the top guys in the world in the first round, just get destroyed.
That's pretty much how it works.
No, it was actually, so I used to play close, this was a body type ago, I broke my back, then I got fat, but I used to play close to professional tennis. I played at University of Illinois in Division I tennis, and so in one of these tournaments, I qualified for the main draw. It was the Indianapolis Hardcourt Championships, and in the first round, I played against, any of you follow tennis? You heard of a guy named Mats Wilander? Used to be number 1 in the world.
You played against him.
Yeah, but not number 1 in the world then.
Yeah.
He was an older guy. He's very old now. But back then, so this was 20 years ago or 22 years ago.
Post his.
Yeah, he was already old.
Okay.
Yeah. But he was, so probably 10 years before that, he was the number 1 player in the world. And now he was just kind of, end of career playing.
And he's still obliterated.
I went in like this. I'm thinking, I'm this top college player. Don't let it go to your head when you beat this old man. He beat me so bad, and I played good. It was amazing how good the best players in the world are. I never had an appreciation for it. He was old. Relative to me, he was slow, and he just dismantled me. And I played well. And he was so nice about it. Afterwards, we sat down. I practiced with him the next day, and he explained to me what I did. He said he knew where I was hitting my next shot 2 seconds before I hit it. He could already just go stand there. So, the body language, it wasn't what he could do physically. He was so skilled at tennis that he could predict what you were doing, your next shot, so far in advance that he didn't need the speed. It's like I couldn't hit a winner. He was just there. It was amazing to me. Probably one of the most humbling things that ever happened to me. Because this hot shot. Kid's like, I'm going to kill this guy. He destroyed me. I was lucky to get a game.
He just shut you out.
Oh, he beat me 6-1, 6-0.
Jeez.
In 35 minutes, 40 minutes. He just wiped the floor with me. Wasn't even close. And I played well.
He's still alive.
Oh, yeah. Still
You
alive.
should email This is what happens.
Well, hey, but my claim to fame is I have an undefeated record against Andy Roddick. Have you heard of Andy Roddick? Yeah, but I'm a little older than Andy Roddick. So I played when I was in juniors. He was a 12-year-old playing up in boys 18s. So I was like one of the top couple players in the country in boys 18s. And get it back. And he was like number 4 in the country in boys 18s as a 12-year-old. So he didn't have 150 mile an hour serve as a 12-year-old, right? Little bit different. That's claim to fame. Never lost to Andy Roddick.
I actually didn't see. Wawrinka won?
Yeah, beat Djokovic.
It was 3-1
What do you mean 3-1?
in terms of games.
Yeah. Well, Wawrinka's good.
Yeah.
It's not like nobody beat him.
Yeah, but I mean, like,
I mean, Wawrinka's top 5 in the world.
More recently, though.
Oh, sure. But it's not like somebody came from nowhere and beat the number 1 player in the world. The number 5 player beat the number 1 player. It's not like shock. You know, and Djokovic is getting old. I think he's 29 now, or he might be 30. That's old for a tennis player.
Well, I mean, isn't Federer still super aged?
Well, Federer's like 34 now, but he's a shadow of what he used to be. He's still 3 in the world. He's injured. I mean, he never was injured during his main career. Now he's injured because he's old. He's a step slower. So where he used to dominate.
Did he play the U.S. this year?
He didn't play. He didn't play in the Olympics either. He had back surgery.
Well, not a lot of.
Well, no, he would have. Yeah, he had back surgery, so he took the rest of the season off. So I mean, he's still one of the best players in the world, but he's not Roger Federer, dominant, can't lose a match. Just like Tiger Woods. I mean, those guys were playing at such a level, and Tiger's coming back next month, and I expect he'll be a very good player once he gets back into it. But will he ever be Tiger again?
No.
Smart money is on no. You never know, but smart money is on no. All right.
And then you got fat.
Let's keep rolling. Let's keep rolling here. Yeah. So.
So you just stop eating it, start eating and never stop.
All right. So in any case, we'll take this version of Linux and miniaturize it so that it can it'll just be a lightweight operating system. We can put in all sorts of different devices. So now, rather than having proprietary operating systems all over the place. A proprietary operating system for the soda machine, a proprietary operating system for the toaster, and a proprietary operating system for the blender. Now we're going to have a micro operating system built on some sort of standard. Most of it's going to be Linux. There's a couple other ones out there, but they're all going to be Unix flavors. Mostly because they're convenient to use through a terminal like this, where Windows wouldn't really be convenient to use from a terminal like this. And DOS really isn't a thing anymore. DOS was never powerful enough to exist as its own modern operating system. DOS took us to a point for the consumer, but then we moved past that pretty quickly. You can do far more from a Linux terminal than you can from a DOS terminal, even though they look similar at a glance.
Do you think Bash being on Windows is going to change that?
Well, only if they maintain the tool set. I mean, Bash is just the shell. It's giving you it's giving you access into the tools that are behind the scenes, like ls and grep and touch and more and less and all the different editors and things like that. All those tools, each of them represents a Lego, just like magic tricks on the CPU that we can use to solve problems. So the number of Legos that are exposed to us in Windows historically is a very small number of Legos. Very small number of magic tricks. So I'm not sure. I know Bash is on. It's on there now, right?
I think so.
But does it have the full? Is it just Bash syntax for writing scripts, or does it have the full suite of POSIX compliant applications behind the scenes? That's the bigger question. So like if I'm here and I type in top, this is going to take me to a thing that shows me the current thing of what's going on in my system load, things like that. So for relating it to us. Here, so on my computer right now, I have 309 programs running, processes running. 2 are running right now. 9 are stuck. A bunch are sleeping. Here's the number of threads that are currently going. Here's the load average on the various cores. CPU usage. So Remember we talked about, I probably mentioned something in here at some point, that our CPU sits there idle 98% of the time or something. So right now, you see I have all these applications open, plus I'm screen recording. Okay? And my CPU is only being used 2% of the time. And this is a computer from mid-2012. Core i7, quad core. So that should be kind of evidence that we're doing, not trivial stuff right here and barely using our CPU. All right? But the point is that with all these commands, you can do pretty powerful stuff from the command line on Linux. So if the tool set is there, it's less about the shell being anything important. It's more about the tool set itself.
They said it gives Windows 10 a Windows subsystem for Linux. So it's like, they said, think of it as the opposite of wine for Linux. So running Windows programs on Linux.
Mm-hmm.
It's just the other way.
Okay.
It's not a virtual machine.
So that's fair enough. That means it's running a Linux microkernel.
Yeah.
So and that's kind of what we're talking about right here. So effectively, Windows is embedding within it a micro Linux operating system for running small command line utilities. Could be web servers, things like that. So that's definitely a perk.
It's the only limit. It says it will not work with server software and it won't work with graphical software. So.
Okay. Yeah, but whatever. The point is that Windows doesn't stand on its own very well because it's very reliant on its GUI. Where Linux, the GUI is an afterthought from day one. When you install Linux on a machine, you can choose to install Linux without a GUI. You don't have to have any graphic user interface. So it's not even about which one's better. Just Linux is the preferred tool for the job because it doesn't rely on as much stuff. It's not consumer facing so much.
I think it's less. I think it was more like you can't use it with like graphic things, like programs made to work with graphics.
Yeah, maybe if that would mean it's emulating it at some level, so you don't have direct access to the graphics card. Right. That could be it. Okay, so in any case, it makes sense to us to go ahead and have that operating system be the same operating system and have the microchip be the same microchip and have us move that from device to device to device, blenders and toasters and things like that, until we finally land on a, so that way we have a standard across the world. So now you can have one person who kind of knows how to fix small appliances, the computing side of small appliances. So think about the IT person. Okay, going in to debug your toaster, okay, instead of the guy who fixes the coil that's burning out of your toaster. Like, well, my toaster just isn't updating the weather.
That should be kind of awesome.
Oh, those exist. Toasters that have real-time weather on it. Yeah, I mean that's
like
that's
on
the
screen, or does it print it on your toast?
Oh.
you get the little weather symbol, like it's gonna
Well,
rain. And it's 64
I think
degrees.
here's the point of this question. I can't, with full confidence, tell you that does not exist.
I know.
Okay, that's the point of the conversation. It very well might print the current temperature on the toast.
Toaster toasts weather on your toast.
All right, let's just finish this conversation real quick so we can take a quick break before our last part of the class. Okay, so it makes sense to us for there to be a common small appliance operating system so that any one of us who's like an IT professional who's going to work on these things sits down and they say, oh, well, I know how to handle this big array of appliances because they all are running the same operating system on the same microchip. Similarly, if it's based on Linux, chances are the next class up of appliances are probably also running on Linux. Similar, but maybe a little bit more powerful microchip, so on and so forth. So we've added a kind of a standardization to that process. Make sense? All right, let's take a 10-minute break. We'll come back, and then we'll do our last portion of the class.